Okay, our next presenter is Fionna Samuels. And again, lots of people knowing they wanted to study what they studied when they were little. She knew she wanted to study chemistry when her high school teacher blew up a trash can with a chunk of sodium. I love chemistry stories like that. And she says, even though I study plant cells, I can't grow a garden for the life of me. So the title of her presentation is Freezing Roots and Shoots, Vibrational Microscopy to Improve Cryopreservation.
Plants represent 82% of life on Earth and approximately a third of the average American's diet. I myself like to indulge in plants by drinking a nice cup of coffee, eating chocolate, or occasionally enjoying a glass of wine. Unfortunately, plants are going extinct at a rate 500 times faster than what we would naturally expect. From rising temperatures, changing weather patterns, and threats like wildfires, climate change is threatening 60% of coffee species, 85% of the land that wine grapes are grown on, and about half of the world's cocoa plantations. What's worse is that these plants represent plants that can't be saved through their seeds, either because the seeds themselves die when they're dried, in the case of cocoa or chocolate, or because the plant is clonally propagated, in the case of grapes. So we have to figure out a different technique to preserve these species, and that could be cryopreservation. So cryopreservation is the freezing of biological materials at liquid nitrogen temperatures, which is approximately negative 200 degrees Celsius. In plants, this means cutting a tiny little piece, usually from a root or a shoot, and freezing it in liquid nitrogen for years or even decades before thawing it and regrowing it into a fully developed plant. So negative 200 degrees Celsius is really cold. There's not a whole lot that can survive freezing at 0 degrees, which is where water freezes, much less negative 200 Celsius. So to ensure that the plant tissue survives the freezing and thawing process, researchers first expose it to cryoprotectants, which are small molecules that help protect the cell. Unfortunately, we don't really know how these molecules are interacting with the live plant cell in order to protect it from these extreme temperatures. So when researchers have to preserve a new type of plant or a new species of plant, they have to rely on a guess and check methodology to create a mixture of cryoprotectants that's tailored to that plant. Now, this is fine if you have unlimited resources, but if you're limited by funding, research staff, or the plant itself is endangered, you don't want to waste resources on guessing and checking your mixtures. And that's where my research comes in. So I use vibrational microscopy, which excites unique vibrations in a molecule to actually image it under a microscope. And using this technique, I've actually been able to observe cryoprotectants entering living plant cells. And my entire project is to develop a technique and a protocol so that we can actually differentiate why some cryoprotectants protect cells while others kill different cells. And this kind of fundamental knowledge is vital when we look at streamlining the process of creating new cryoprotectant mixtures so that we can maximize the number of plants that we can preserve as we face this climate crisis ahead of us and ensure that our world stays lush and beautiful and we can enjoy the simple pleasures of plants for years to come. Thank you.